Hello. We are going to talk about chapter 14 in your book, and it's aqueous equilibrium, acids and bases. And what you'll notice right away when you look at the chapter is it's just a specific example of a chemical system, so acids and bases, and it's just equilibrium. So the ideas that we learned in chapter 13 should just be emphasized here. So, share the screen. Okay, so it's chapter 15 in the new edition, but chapter 14 in your book. And okay, so there are several definitions of acids and bases. The one that you would have seen in Chem 107 is the Arrhenius definition. So it's really specific. It's an acid is a substance that dissociates in water to produce hydrogen. So that's very, very specific. An Arrhenius base is a substance that dissociates in water to produce hydroxide ion. The one we're going to use more in this chapter is called the Bronsted-Lowry theory. And in this theory, it's a little more general. An acid is a substance that can transfer hydrogen ions, in other words, a proton donor. And a base is a substance that can accept hydrogen ions, in other words, a proton acceptor. So when you look at a reaction of an acid with a base in this equation, the left-hand side has an HA, so that molecule is an acid. It can donate that proton, so the hydrogen can come off, leaving its electron behind, so it's just the proton. The B for base is what will accept it. So on the left-hand side, the pink is the acid, the blue is the base. On the right-hand side, now the base has picked up that proton, so it becomes an acid, and the acid has given up the proton, so it's just left as A minus, and so now it would be a base. So these are conjugate pairs, so conjugate acid-base pairs in the Bronsted-Lowry theory, where the HA is the acid. When it gives up its proton and it's A minus, then that's the conjugate base of that particular acid. So the same thing with the base. It's a base on the left-hand side. When it picks up the proton, it becomes an acid, the conjugate acid of that base. So within this theory, this is just a more visual way to look at what's going on. So if we have HA and water happens to be the base in this situation, then water can take the H plus off of the HA and become an acid, and it leaves behind A minus, which is now a base. So the conjugate acid-base pairs are shown on the bottom of the slide, where the HA is the conjugate acid of A minus, the base, and water is acting like a base here, and the conjugate acid is H3O plus. You can have the same exact situation. So when you talk about a base in water, base dissociation equilibrium, we have something like NH3, ammonia, and it reacts with water. But now water is going to act like the acid, and the ammonia will be the base. So notice that the ammonia picks up a proton, and by picking up a proton, taking it off of water, it's created OH minus. So this wouldn't be an Arrhenius base because it didn't dissociate in water to make OH minus. It rather reacted with water in an acid-base reaction, picked up a proton, leaves behind OH minus, which is a base. So the bottom of the slide shows you the same thing. You can have a weak base reacting with water, but now water will act as an acid, and the base of the conjugate base of water will be OH minus, and the conjugate acid of this weak base will be the ammonium cation. So the relative strength, if you have reactants and products, if you have equal concentrations of reactants and products, which direction will the reaction go? It always goes from stronger acid, stronger base to weaker acid, weaker base, which makes sense. If something's a stronger acid, it's going to be able to give up that proton easier. and a stronger base will be able to pick it up easier. So the reaction will go in the direction to form weaker acids and weaker bases. So this is just a picture that a more visual of the strength of acids. So an acid that's only partially dissociated in water and is only a weak electrolyte, because we know when it dissociates in water, it makes charged particles. You may remember from Chem 107, electrolyte is anything that has charged particles because they can carry electricity. So the first in this schematic is what you would think of as a strong acid. So if HA is a strong acid, you put it in water, all the HA goes away, and you create H3O plus and A minus. If it's a weak acid, that only partially happens, and the HA, some of it stays together, some of it forms H3O plus and A minus. So you have a weak acid where there isn't 100% dissociation. A weak base is the same thing, where, a very weak acid, sorry, this is still the acid slide. And now they're just showing you if it's really, really weak, then you barely make any H3O plus and A minus, and almost all of it just stays together as A minus, or HA, sorry. So this is just a little table. There's a Ka table at the back of your book that you'll get used to using that gives you actually numbers for the equilibrium constants. So when we think about this slide, the equilibrium constant for the second and third picture here, the weak acid and the very weak acid, you'd have to know the equilibrium constants for those dissociations in order to know how much H3O plus you produce in water, so how acidic a solution is. And this just shows you some of those acids and their relative strengths. So on the left-hand side, the strong acids are at the top, the weak acids are at the bottom. And on the other side, the base of a strong acid is always a very, very weak base. Because if you think about it, if something like HClO4 or HCl completely dissociates in water, then it's not going to be very likely that that conjugate base, the ClO4 minus or the Cl minus, would pick up a proton and go the opposite direction. So strong acids have very, very weak conjugate base, and weak acids have strong conjugate bases. So this just shows you that in Chem 107, we often just represented an acid as producing H plus, the Arrhenius definition. But when H plus is in water, it wouldn't stay all by itself. If you think about what H plus is, it's simply a proton. It's a charged, very positively charged particle, and would like to be surrounded by negatively charged particles. So it's going to be hydrated by water molecules. H3O plus would be if it has 1. When you have 2, it'd be H5O2 plus. So there are lots of different hydrated forms of H plus, but we'll just generalize it, and we'll call H plus H3O plus, meaning that when it interacts in water, the water always forms a partial hydrogen bond with that H plus. So this particular section in your book is actually 14.15, the factors that affect an acid. So how do you look at an acid or look at a molecule and decide whether or not it's going to be a strong acid? And we're going to come back to this after we do thermodynamics. So you can skip that section right now in your text. Okay, so water by itself is interesting. So if you just have a tub of pure water, what you actually have is mostly water, mostly H2O, but a little bit of water dissociates with itself. So one of the water molecules can act like an acid. One would act like a base. So one would give up a proton, one would give up a proton, and you get H3O plus and OH minus. So this dissociation of water is shown in the reaction right in the middle. So if you have 2 water molecules, one can pick up a proton, one can give up a proton, and you form H3O plus and OH minus. If you look at this, this is the first equilibrium constant we'll see. So it's called the ion product constant for water. So it's given it's just a K, but it's labeled with a W to tell you that it's a specific K for a specific reaction. So if we look at that reaction for the dissociation of water, the products over the reactants, water is a liquid on the reactant side, so that's left out. So the K for that reaction is just the H3O plus concentration times the OH minus concentration. So you would have known how to write that equilibrium constant in chapter 13. And here we're just seeing that for this specific chemistry, the acid-base chemistry of water, we're going to give the K a special name. At 25 degrees, this value is 1 times 10 to the minus 14. So that tells you not a lot of water reacts with itself. If you have a flask of water, it's mostly water. A little bit has undergone this acid-base reaction. So because of this equilibrium, we can always figure out the H3O plus concentration if we know the OH minus and vice versa. So on the left-hand side, if you know the OH minus concentration, you can divide the Kw by that concentration to get H3O plus. And on the right-hand side, the opposite. If you know the H3O plus concentration, the hydronium ion, you can calculate the OH minus. So this equilibrium expression is always valid, even if you don't have pure water. So this is just showing you that if you have pure water, you have a neutral solution. So you would go back here, and on the bottom slide, you would know that the H3O plus has to equal the OH minus if it's just pure water, and the source of all hydronium ion is water dissociation, and the source of all OH minus is that same reaction. Then they'll be equal to each other, but you may have introduced some acid. So maybe you put a drop of HCl in that solution. Well, then you'd have the left-hand side where you have more H3O plus. Because of that equilibrium, that forces, if you add some H3O plus, that forces the equilibrium backwards, and that means that the OH minus concentration is less than 1 times 10 to the minus 7. Same thing if you added some base, it would force the reaction backwards through the Chatelet's principle, and you'd get less H3O plus. So an acidic solution by definition is one where the hydronium ion is greater than OH minus, neutrals when they're equal, and basic by our definition is when H3O plus is less than OH minus. So these are usually small negative numbers that you're dealing with. And so the pH scale just makes it easier to tell someone what's in the solution with numbers that are easier to deal with. So by definition, the pH is the negative log of the hydronium ion concentration. So if we have a neutral solution where the hydronium ion concentration is 1 times 10 to the minus 7, if you take the negative log of that, so take the log and then change the sign, you will get 7. So the pH of a neutral solution is 7. The pH of an acidic solution is less than 7. The pH of a basic solution is greater than 7. So with the pH scale, we have a new math formula. We're going to use log, and when you use log, you have to think about a new rule for significant figures. So this tells you that lemon juice has a concentration, or that the hydronium ion concentration is 0.0025 molar, and they want us to calculate the pH. So 0.0025 molar has 2 sig figs. Remember, those zeros aren't significant. When you take the log, you end up with 3, because the 2 significant figures are how many significant figures you'll have to the right of the decimal place. And the 2 in the 2.60 is considered an exact number. So that's the base 10 that you're looking at. So want to make sure that you learn this rule and use it always. So calculate the pH of an aqueous solution that has an OH minus concentration of 0.0019. So you could get the H3O plus concentration by dividing Kw by OH minus. That's what this slide showed you. So if you want the H3O plus on the left-hand side, but you know the OH minus, you just divide it, the Kw by that value. And when you do that, you get a low concentration for H3O plus, 5.3 times 10 to the minus 12. When you take the negative log of that, the number had two significant figures. So we have 2 to the right of the decimal, and the 11 is essentially the base 10 that you're talking about. So that's an exact number. Acid rain has a pH, in waters having a pH lower than 4.5 to 5. Calculate the hydronium ion concentration in a lake that has a pH of 5. So now we're going the opposite way. So our pH only has one significant figure to the right of the decimal. That means that our hydronium ion concentration is going to have one significant figure. So to take the inverse of the pH, if pH is the negative log, then we're going to change the sign and take 10, raise it to that power, because that's the inverse function. So the hydronium ion concentration will be 10 to the minus 4.5. There's one significant figure to the right of that decimal, so we have one significant figure in our concentration. So before you go on to this slide, take a little break, pause the video, go to page 549, and do problem 1411. So on page 549, take a little break and do that problem that just asks you to calculate pH 1411. Come back and I will be here. So when we measure pH, one way you can do it is with an indicator, a molecule that changes color based on whether or not it's protonated. So you'll use pH, or you'll use indicators in lab. This just shows you that indicators will change their color at different pHs. So you're going to have to realize that and think that with each of these, when, for example, phenol red changes color from yellow to red, you're at a pH of 7. So each of these would be useful if you're looking for a different pH change. So now we're going to talk about the equilibrium of acids and bases. So we're first going to talk about strong acids and bases. So remember, those were situations where you said the reaction went to completion when you reacted the acid with water. And so this is showing you that rather than having an arrow going forward and backwards, thinking about equilibrium, the equilibrium really lies on the product side. So we'll put an arrow in one direction. So if nitric acid, HNO3, is a strong acid, that means when you put it in solution, if you put in 0.025 molar, what you've really put into solution is 0.025 molar hydronium ion. So when you determine the pH of that solution, the pH is easy to find because every single acid molecule should have dissociated, so you know the H3O plus concentration directly. Strong, so this is a strong base. So what's the pH if you have the same concentration, but it's a strong base? So with a strong base, something like sodium hydroxide, we also draw a one-way arrow. It's the same thing as saying sodium hydroxide completely dissolves in water. And every sodium hydroxide that you put in will become an OH minus anion. So the concentration of OH minus will be equal to the concentration of sodium hydroxide that you put into the solution. In order to do the pH, you want to get the H3O plus. So Kw divided by OH minus gives you the hydronium ion concentration. Then you'll take the negative log. We have 2 sig figs in our concentration, therefore we'll have 2 sig figs to the right of the decimal, and the pH will be 12.4. When we have weak acids, just a minute. So before you go on to weak acids, stop and take another break. On page 552, there's a problem 1412. Just asked you to do a calculation like this where you get the pH for a strong acid. Then come back and we'll talk about the equilibrium of weak acids. So with weak acids, we're going to have to start using what we know from chapter 13. So if we have something that's a weak acid and it dissociates in water, you have to draw the two-way arrow, meaning some of it will react forward and make hydronium cation and the conjugate base of that acid, A minus, but some of it won't dissociate. So that just depends on how strong the acid is. The more H3O plus it makes, the stronger the acid. When you were to write an equilibrium constant for this reaction, if you were back in chapter 13, you'd put products over reactants. You'd leave out any liquids and solids. And so you get a K. In this case, it'd be the hydronium ion, the A minus, divided by HA, because water's a liquid. And that's just an equilibrium constant, but we give it the subscript A so that we recognize it as an acid dissociation constant. So the equilibrium constant for an acid dissociating in water. This just gives you some numerical values for a few of them. So at the top, something like hydrochloric acid, which we said was strong, you're essentially saying it goes completely to completion, 2 times 10 to the 6. So almost all of the HCl reacts to form H3O plus. But you can get way, way, way weak acids. So if you look at something like methanol, its Ka is 2.9, the bottom one on this table, times 10 to the minus 16. Very, 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 very weak. So if you put methanol in water, most of it stays together and very, very, very few protons come off as acidic protons to make hydronium cations. So we're going to do problems just like we did in chapter 13, where we're going to use an icebox. So this says, what's the pH of a 0.250 molar solution of HF? And looking back here, HF is the third one, and it's a weak acid, so it doesn't dissociate completely. And so it gives us the pH, and it wants us to figure out the Ka. So we know that if we put in 0.250 molar, we start out with approximately 0 H3O plus and and 0 F minus. Some of that reaction will go forward, so negative X, and then on the product side, every HF that dissociates forms 1 H3O plus and 1 F minus, so that's plus X for each of those. So when we look at what X is based on our pH. So we know that the pH is 2.036. So that means X is 10 to the minus 2.036. So the hydronium ion concentration in this solution is 0.00920, and the fluoride concentration is the same. So we can use that information to plug into our expression for a Ka. So both the F minus and the hydronium ion concentration are the same. The F, or HF, is 0.250 minus that, and so doesn't change it much, but it's down to 0.241. So if we just put those concentrations into our equilibrium expression, we can solve for Ka, and in this case, get 3.51 times 10 to the minus 4. A pKa is the exact same thing as a pH, except it's a p and the negative log of the Ka. And that's an often common way to express the strength of an acid is with the pKa rather than the Ka, because they're easier numbers to deal with. So we're going to take the negative log of the Ka, and we had 3 sig figs in our Ka, so we'll have 3 sig figs to the right of the decimal in our pKa. So the pKa for HF is 3.455. So you can use the equilibrium constant, if you have it, to calculate concentrations. You can use concentrations to calculate the equilibrium constant. So this one asks you to calculate the pH of a solution if you know the Ka and what the acid is. So if we put in 0.10 molar HCN, and it's a weak acid, the Ka is pretty small, 1.4 times 10 to the minus 9. Some will react forward, plus X and plus X. The HCN will go down, minus X. So when we put that into the Ka expression, we have x squared over 0.10 minus x. And notice with a Ka so small, 10 to the minus 10, not very much dissociates. So we're going to make the approximation that when you subtract x from 0.10, it won't change 0.10. That makes it really easy to solve. And when you solve it that way, you get an x value of 7 times 10 to the minus 6. And you can go back and confirm. If you subtracted 7 times 10 to the minus 6 from 0.10, or from 0.10, yes, it wouldn't change 0.10. So that was a good approximation. So you'll be able to use Mathematica on the test, but sometimes it's just makes more sense to save some time. We didn't have to plug that into Mathematica. So with this, if we want to know the pH, just take the negative log, we get a pH of 5.15. So this just is a flow chart of how you're going to calculate a pH with a weak acid. And so before you go on, go ahead to page 558 and do problem 14.17. It's just, well, you'll use the equilibrium constant for a weak acid. This one just is giving you a definition that's often useful, the percent dissociation in a solution of a weak acid. So the percent dissociation tells you about the strength. So it's by definition how much of the HA dissociated divided by how much you put in times 100. Okay, so now we're going to talk a little bit more about weak acids and acids that have more than one proton that are acidic. So this is carbonic acid, and you can look in the back of your book. There's a table of Ka values in the appendices. And when you looked at it, you would see that for carbonic acid, they give you 2 different Kas. That means that 2 of those protons can react as acids in water. So when the first one comes off, the Ka is 4.3 times 10 to the minus 7, so a pretty weak acid. When the second one comes off, it's 5.6 times 10 to the minus 11, so much, much weaker, that second proton coming off. And that will always be the case. Taking a second proton off of a weak acid will always happen less. You'll have less dissociation of the second one. So here are some of the polyprotics. If you look in your table at the back of your text, you'll see all of them. Phosphoric acid actually has 3 protons. So we have everything else is diprotic, but phosphoric acid is actually triprotic. So if you want to calculate the pH in a solution that's polyprotic, what you'll notice is that the most important source of the H3O plus is the first proton coming off. So we'll use the first Ka, and then we'll confirm that afterwards. So with the first Ka, you can figure out that the H3O plus concentration from that first proton coming off is 9.3 times 10 to the minus 5. That will determine the pH, but we'll confirm that here in a second. Oops. Guess they are not going to have you confirm it. There'll be problems in the book where you'll confirm it, and we can do one in class too, where if you look at the second proton coming off, you will see that barely any come off compared to 9.3 times 10 to the minus 5. So the pH for a polyprotic acid will always depend on the first Ka. That's the most important source of hydronium. Okay, so need to talk about weak bases. It's all the exact same concept of equilibrium. So if we have a weak base reacting with water, water is going to act as the acid. The base will pick up a proton and leave behind OH minus. So it's an equilibrium constant for that reaction. We'll give it the subscript B because it's for a weak base dissociating in water. So something like ammonia we talked about earlier, when it reacts with water, you make the ammonium cation, leave behind OH minus. So the Kb expression would be the ammonium cation concentration times OH minus concentration divided by the ammonia concentration. Here are some values for some of the weak bases. And the conjugate acid of that, it gives you what the Ka is. So shows you that the stronger the weak base, the weaker the conjugate acid strength. So if we make a solution with a weak base, we use exactly the same concepts from chapter 13 that we used with weak acids. If we want to calculate the pH in this solution of ammonia, and we have the Kb, set up an ice box. If you put in 0.40 molar NH3, some will dissociate forward, so you'll have minus X. You'll make X amount of ammonium cation and OH minus. So when you put that into the Kb expression and solve for X, now X is OH minus, and so you have to have one more step. You have to take the Kw and divide it by the OH minus in order to get the H3O plus. And then once you have that, you just take the pH just like you've been doing in the past, and you'll have 2 sig figs to the right of the decimal. So before you go on to this slide, take a look at page 564, problem 1422. It's one on weak base equilibrium, and then come back and we'll talk a little bit more. We're almost done with the chapter. So if you know the Ka or the Kb for an acid-base conjugate pair, then you can always determine the other one. So when you look at these reactions, the first one is the acid dissociation of the ammonium cation. The second is the base dissociation of ammonia, which if you refer back to the first reaction, that's the conjugate base of ammonium. And ammonium is the conjugate acid of ammonia in the second reaction. If you add those two together, you get just the equilibrium of water. So if you add those two reactions happening together, then the NH3 cancels from both sides, and then NH4 plus cancels from both sides. So that means that Ka times Kb equals Kw. So you could also write it out this way, but you know from the relationship between Ks from chapter 13 that this will be true. But it's just showing you here in the second to last line that the Ka would be H3O plus times NH3 over NH4 plus. The Kb would be NH4 plus times OH minus over NH3. When you multiply those two expressions, all you're left with is H3O plus and OH minus, which is Kw. So that means if I had a table and it had the Kb for NH3, I would know the Ka for NH4 plus just by the relationship in the last line. So this is just emphasizing that Ka times Kb equals Kw has to be for the conjugate acid-base pair. So if you have one or the other, you can solve for the one you're interested in. This also just shows you that you can take the pKa plus the pKb to get pKw. So I'm not sure. That might be useful sometimes. I've never used that last equation. Okay, so we'll continue with salts. This will be our last big section. So if you have a solution that has some ionic compound dissolved in it, sometimes the cations and anions will be acids and bases. So we want to think about what happens when we put a salt into water. Will it make it acidic, basic, or neutral? So the following, okay. Okay, neutral solutions, this slide is talking about. If you look on page 570, there's a table that summarizes how you look at ions. So that's probably a table you might want on your note card. So page 570 has these next few slides summarized into a table. So if you have a cation from a strong base, it's going to make the solution neutral. So the way you think about that is, for example, if sodium hydroxide dissolves in water, we say it's a strong base, so it goes completely forward to Na plus and OH minus. Well, if it's going to go completely forward, that means it's not going to react backwards if it's in solution by itself, the Na plus. So all of those cations from strong bases will make neutral solutions. And anions from strong monoprotic acids will make neutral solutions. So if HCl is a strong acid, then when you put it in water, it completely dissociates to make H3O plus and Cl minus, which means the Cl minus would not react backwards. Anything that's going to yield an acidic solution. So if you put ammonium chloride into solution, NH4 plus is a weak acid, so you'd be able to find that in your table. So that's clearly going to make a weak acid solution. If you put NH3 into solution, it's going to be a weak base. So if you look at the cations and anions that you're putting into solution, you'll know whether or not they have acid or base properties. Don't worry about the metals. These are examples of Lewis acids, so we're not going to worry about those. I'll talk in a minute about that. This is just another example. If you're going to make a basic solution, if HCN, the product in this reaction, is a weak acid, that would mean that if you put Cn minus into solution with sodium cyanide dissolving, that weak base, the Cn minus, which is the conjugate base of HCN, will act like a base in that solution. Salts that contain acidic cations and basic anions. When that's the case, then you have to decide which is the stronger of the two. So in this ammonium carbonate, NH4 plus is a weak acid, CO3 2 minus is carbonate. That's the conjugate base of the weak acid carbonic acid. So that's a weak base. So the way you figure it out is you look at the Ka and the Kb. So the Ka for the NH4 plus in water does not give it to us. And the Kb for the carbonate, if you look at those two values, if the Ka is bigger than the Kb, the solution will be acidic. That makes sense. That would say that the weak acid you put in is a stronger weak acid than the weak base is a weak base. If the Ka is less than the Kb, the solution will be a weak base, and so it'll be a basic solution. If they're about equal to each other, the pH should be 7. So now, yeah, they do give them to us. So if we compare the Ka for NH4 plus, so we use the Kb from the Kb table for NH3 to get a Ka. So the Ka for NH4 plus, 5.6 times 10 to the minus 10. The Kb for carbonate is the second, or yeah, if you calculate it, you will get 1.8 times 10 to the minus 4. So we used the Ka for H3O plus because this is the conjugate base for the second proton coming off of carbonic acid. So this Kb is bigger than the Ka, so this solution is going to end up being basic. So this is the table that I was talking about. In your book, this table is on page 570. So take a look at that table. You might want to put it on your note card. Okay, there's one last definition of acids and bases that is more general than anything we've used so far, and you might run into this in organic chemistry. So a Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. So when you look at the proton here, acting as an acid, it can accept that pair of electrons on ammonia, which is acting as a base and donating that pair of electrons. So it's the only thing I want you to know about Lewis acids and bases is just the definition. The rest of it you can skip. So take a break now. This is the end of this chapter. And just look on page 570 and do problem 14.27. Skip D, so problem 27 on page 570. Skip D because that's an example of a Lewis acid base. So do all the other ones where you're asked to determine if the solution is acidic or basic. So that is all of chapter 14. I'll come back in a little while and do some problems.